today we're going to be discussing special angles. Now, special angles are those angles whose trig ratios can be computed easily with the use of diagrams, meaning that you wouldn't need a calculator to compute those trig ratios. So the most common or the special angles that are often used are 30 degrees, 60 degrees, and 45. So if you had to look at any textbook or even do a Google search, these three angles would come up immediately. Today I'm also going to be discussing 0, 90, 180, and 270 degrees. Right, so today let's start off with 0, 90, 180, and 270. So that's what we're going to be discussing with the aid of this diagram. 0, 90, 180, and 270. So if we look at this Cartesian plane, the xy plane, if we take the positive x-axis to denote 0 degrees, then observe that the positive y is then 90, the negative x is then 180 degrees, the negative y-axis is then 270 degrees, and of course the positive x could then be interpreted as one revolution of 360 degrees. Right, so now let's suppose that we draw a unit circle. A unit circle is a circle with radius 1. So we draw a unit circle where radius equals to 1 and origin at the center. Right, so the coordinate 0, 0 will be the center of the circle, being the center. Right, so I'm just going to quickly draw this circle. Right, so do my best to let it look as perfect as possible. So I'm aiming for radius 1. Right, so assuming that looks perfect. Right, so remember, since radius is 1 and center is origin, if we look at where this circle intersects all of the axes, then this x-intercept will then have a coordinate. Remember, radius is 1. So the distance from the origin to that point is also 1, which means that x is equal to 1 and y is 0 because this is an x-intercept. Similarly here, since this is a y-intercept, we have that x is 0, and since radius is 1, then the y-coordinate is 1. If we look at this x-intercept, since radius is 1, we then have that coordinate is negative 1 with y-coordinate equal to 0. And finally, this y-intercept here would then have coordinates 0 and minus 1. So we've drawn a unit circle on the xy plane, and we've now labeled the points of intersections that have occurred. So using this diagram, you will now observe that we will be able to compute the trig ratios at each of these degrees, 0, 90, 180, and 270. I think it will be firstly important to note our acronym, so CARTOA. And let's start off with 0 degrees. So if we had to start off with 0 degrees, then we would want to compute sine of 0 degrees, cos of 0 degrees, and tan of 0 degrees. So this is what we would want. Now remember, in our previous video lecture, when we had drawn our triangle on the xy plane, we then obtained another interpretation of our trig ratios. So opposite over hypotenuse for sine then translated to y over r, where your r was the length of the hypotenuse, or the radius of the circle, and we know that our radius of our circle in here is 1. For cos, it's car adjacent over hypotenuse, that translated to x over r. And for tan, toa, opposite over adjacent, translated to y over x. So I'm now using the interpretation that we had obtained from the xy plane for this. And since we now have all of our ratios, what do they now equal to? What is y? So if we're looking at 0 degrees, we are working with the coordinate 1, 0. Y is 0 and our r is 1. So that means sine of 0 is 0. If we're looking at cos of 0, we need x over r. What is the x coordinate? That was 1. So that's 1 divided by radius of 1. And our answer is 1. And tan of 0 is y over x. So looking at our coordinate, x comma y. So remember, in this case, I am working with that coordinate when computing these ratios. So x comma y is 1 comma 0. So therefore, this is 0 divided by 1, giving me a final answer of 0. It's important to note that the interpretation at 0 and 360 degrees is exactly the same. So that means that this is also sine of 360. This is also cos of 360. And this is tan of 360. So we can now move to compute at 90 degrees. Remember, our coordinate here at 90 degrees is the pair 0, 1. So if we're computing sine of 90, cos of 90, and tan of 90, and if we are using our interpretations from before, that sine of an angle is y over r, cos of an angle is x over r, and tan of some angle is y over x. What do we now obtain? So remember, we are working with the coordinate 0, 1, so y has a value of 1, r has a value of 1, so cos of 90 degrees is equal to 1. Cos of 90 is x over r, the x coordinate is 0, our radius is 1, so that means cos of 90 is 0. Tan of 90 is y over x. Y is 1 and x is 0. So I now have 1 divided by 0, but remember, this is not allowed, it's undefined. So that means tan of 90 is undefined. And similarly, we could then continue to compute the trig ratios at 180 and the trig ratios at 270. So if we had to compute this for sine of 180 degrees, cos of 180 degrees, and tan of 180 degrees, as we had done before using the same interpretations and this new coordinate from the diagram, then if you did this as an exercise, you will then obtain the final answer of 0 minus 1, because remember, look at the coordinate you're now working with, it's a negative, and tan of 180 is equal to 0. Similarly, if you had to perform the exercise for 270 degrees, then sine of 270 degrees is equal to negative 1, cos of 270 degrees is equal to 0, and tan of 270 degrees is then undefined. Right, so this is actually a very important diagram to have in your arsenal when required to calculate trig ratios of 0, 90, 180, and 270. Let's now consider the case of 30 and 60. So that's what I'm now moving on to. Right, so in the case when we're looking at the angles 30 degrees and 60 degrees, in order to understand this, let's begin with an equilateral triangle. Right, so we're going to study this with the use of an equilateral triangle. Remember, an equilateral triangle is a triangle in which the three sides have the same length, right? So those sides have equal length, and the three angles are also equal. So let's consider an equilateral triangle with side lengths 2. So if I had to label the vertexes of this triangle, let me call this P, let me call that Q, and this R. And since we have side lengths 2, that means the length of PQ is 2, the length of PR is also 2, and the length of QR is also 2. So we have that in place. In addition, since it's an equilateral triangle and the triangle has a total of 180 degrees, it means that angle Q must be 60, angle R must also be 60, and angle P must also be 60. So in an equilateral triangle, it is known that the angles at the three sides must all be equal to 60 degrees. So this is what we have. So now what we're going to do, now going to go a step further, is we are going to draw a perpendicular bisector. I will explain shortly what this is. So we're going to draw a perpendicular bisector from vertex P to the side QR. So here is vertex P and here is the side QR. By a perpendicular bisector, it means we're going to draw a line that is perpendicular to QR, meaning when it reaches QR, it's going to be drawn at an angle of 90 degrees. And by a bisector, it means that it will split the side QR exactly into two halves. So it starts from P, and we draw a line perpendicular to side QR, which splits side QR into two equal halves. So since the length of QR was 2, the equal halves will then have lengths 1. So essentially what happens is we have now created a new triangle. Right? So let's draw our new triangle. The new triangle looks as follows. It's going to be a right angle triangle. So I'm just drawing 1/2. So the new triangle I am considering is 1/2 of the above equilateral. Right, so I'm going to work with PQ and I'm going to label this point S. So I'm working with triangle PQS. It's a right angle triangle. We know that PQ has length 2. We know that QS here has length 1. The length of PS is unknown. We know that angle Q is 60 degrees. This is 90, so therefore this must be 30. Alternatively, since we had a bisector, this would have split into two. This angle would have also split equally into two halves. So the 60 then drops down to a 30 degree angle. So I now have triangle PQS. What is unknown to me is PS. I would like to determine the length of the side PS, and how would we do that? Remember, we are working in a right angle triangle. In video 1, I had recapped on the theorem of Pythagoras, and that is what we will use right now to determine the length of side PS. Right, so what did the theorem of Pythagoras tell you? It told you that the square of the hypotenuse, which is PQ squared, is equal to the sum of the squares of the other two sides. So the PQ squared is equal to QS squared plus PS squared. We want to solve for PS, so I'm going to rewrite it in terms of that. That means that PS squared is then equal to, so remember that's what I'm solving for, it's equal to PQ squared minus QS squared. And what do we have? What is PQ? PQ is 2, so that's 2 squared. What is QS? QS is 1, so it's minus 1 squared. So PS squared is 2 squared minus 1 squared, which then means that PS is the square root of 2 squared minus 1 squared, giving you a value of the root of 3. So that means that this side has length root 3. And we now have a completed right angle triangle with angles 60 and 30 degrees. And notice now that we can now interpret all of the trig ratios. So let's interpret the trig ratios for 60 degrees. Sine of 60, cos of 60, and tan of 60. What do these give us? So remember so katoa, let's write that down. Right, so that means sine is opposite over hypotenuse. Opposite over hypotenuse gives us a value of square root 3 over 2. Cos is adjacent over hypotenuse, and adjacent over hypotenuse for 60 degrees is 1 over 2, and tan, TOA, is opposite over adjacent, and interpreting that, opposite over adjacent is square root 3 divided by, let's just double check that, we're looking at 60 degrees, tan of 60, opposite is square root 3 over 1, and that's what we have in there. Alright, so that means this is now square root 3. Is that correct? Let's just double check. Tan of 60. Here is 60 degrees. The opposite is root 3. The adjacent is 1. Right, so based on our definition, that is now correct. Let's now look at the trig ratios for 30 degrees. So we now want sine of 30, cos of 30, and we want tan of 30. Right, so using our same interpretations, opposite over hypotenuse. Here is 30 degrees. Which side is opposite 30? It's QS, so that has length 1. The hypotenuse is 2. Cos of 30. So remember, we need adjacent over hypotenuse. If that is 30, the adjacent side has length root 3. The and over hypotenuse, that has length 2. And finally tan, which is opposite over adjacent. So if this is your 30 degree angle, the side opposite, that is QS with length 1, and the side adjacent to 30 is root 3. So that means tan of 30 degrees is 1 over root 3. So that is the trig ratios for the special angles 30 and 60. Let's now finally look at 45 degrees. Alright, so write down the page. So now we're looking at our third case, 45 degrees. In the case of the 45 degrees, we are actually going to look at an isosceles, right-angled triangle. Alright, so recall that an isosceles triangle is any triangle in which two sides have equal length, or correspondingly we have that two angles are equal. So consider an isosceles triangle with length 1, right, where the equal sides have length 1, right, with equal sides having length 1. So that means if I draw the following triangle, so it's a right angle triangle, two sides are equal and they have length 1. So here are my equal sides with length 1. I'm going to label the vertices A, B, and C. So side AB has length 1 and side BC has length 1. Right, so since this is an isosceles triangle and it's a 90 degree, so it's a right angle triangle, that means that these two angles must be equal since it's an isosceles. There's 180 degrees in here, we subtract the 90, I'm then left with 90, and therefore this must then be 45, and that must then be 45 since they are equal. Alright, so what is unknown to us? The unknown aspect in here is AC. I do not know what the length of AC is, and once again we will use the theorem of Pythagoras. Alright, so what did the theorem of Pythagoras tell you? It told you that the square of the hypotenuse, meaning AC squared, is equal to the sum of the squares of the other two sides. So it's AB squared plus BC squared. So this means that AC squared is equal to 1 squared plus 1 squared. So AC is equal to square root of 2. So that was the unknown length that we required. And now that we have a complete triangle with all three sides known and all of the angles known, we could now compute the trig ratios at 45 degrees. So I can now compute sine of 45, cos of 45, and tan of 45. Right, so once again, sol katoa. Sine is opposite over hypotenuse. Right, so you could use any of the 45s, it would not matter, you will still arrive at the same answer. So if I work with this 45 as my reference angle, the side opposite it has length 1, and the hypotenuse has length root 2. Cos of 45, adjacent over hypotenuse. Right, again using this 45 as my reference, the side adjacent to it has length 1, and the hypotenuse length is root 2, so we've got 1 over root 2. And finally tan, TOA, opposite over adjacent. Right, if we're looking at that, again using that as my reference angle, the side opposite 45 has length 1, and the side adjacent to 45 has length 1. So the final answer is 1. And so these are the trig ratios using the angle 45 degrees. So it is important that you have these diagrams in your arsenal. So make sure that you remember them at all times. So these are diagrams for special angles. Right, so the first one, remember, this was used for the angles 0, 90, 180 and 270. The second diagram was used for the angles 30 and 60, and the last one was used for 45 degrees. So it's important that you memorize these diagrams and that you know how to interpret them, because from these diagrams you could determine any trig ratio for any of these angles. So how would you be tested on special angles? Firstly, you need to use these diagrams when asked to calculate without the use of a calculator. Right, so in the exam in particular, there will be questions where they will test you without the use of a calculator, meaning that you have to show and give explanations at each step. And one of the explanations would be to provide your diagram on the side, so they know that you have done the computations with the aid of a diagram. Right, so you need to use diagrams when asked to calculate without the use of a calculator. So that's important. So what will these questions look like? So I'm going to provide you with applications of this in the next video. Right, so we'll look at applications after we cover the section on reduction. Right, so that's where I'm going to end today. Applications will be reviewed in the next video.